Hey guys, so today we're going to be dealing with related rates. Related rates is a application of what we've learned in calculus so far. So if you'll be using, the stuff you learned, and especially the chain rule, and solving what you could say is real world problems. And so this is something that a lot of students, a lot of first year students, if it's your first time taking calculus, they really hate because they're really not used to applying the mathematics they've learned. So this comes as a very big new different idea, and it really confuses students because they just don't have that experience with word problems, because that's what you're going to be dealing with in related rates. Um, so it's good to get comfortable with word problems, doing a lot of practice with related rates if you really want to do well in it. And I'll be doing a few videos of different examples, and they'll be shorter videos because like I said, related rate takes a lot of practice, and these problems are word problems, so they take a little more time to solve. So let's get into it. So what is related rates? What if you're seeing this for the first time? What is it? Well, related rates is usually, it's presented as a word problem. And this word problem, the main idea of it is to find the rate of change in one quantity in terms of another, in the rate of change of another, more specifically. I'll show what that means in a second when we get to the example, but I want you to really look at the second bullet here, and this is usually the main way to go about most related rates problems. It's the simple backbone of solving most of these problems is, finding a relationship between two variables, the variables that are in your question, and then differentiating with respect to time. Like I said, you are finding the rate of change in one quantity in terms of the rate of change of another quantity. So you're going to be differentiating using the chain rule with respect to time. And that's very important. So you should really always keep that in the back of your head when you are going through these problems, because you should never try to memorize how to do like different types of problems. I'm doing examples in these videos, so you guys can follow along, get a hang of it. But you should never try to memorize all these different types of questions. There are common ones, like I'll show you, like the sphere, cones being filled with water, um, rectangular. Actually, I can't think of any other on top of my head, but you should never try to memorize. Oh, the ladder. You've probably seen that if you are. Is this not your first time doing this? So you've probably seen that the ladder. That's a really popular one. But like I said, you should not get mixed up in trying to memorize all these different types of problems. So let me show you guys, an example in this video of what I'm talking about. And I'm going to go slowly. I'm going to illustrate everything. And this example is, compared to more sophisticated related rates problems, isn't really that hard, but it's simple enough to illustrate the concept of related rates. So what do we have here? Well, we have this question that's saying helium is being pumped into a spherical balloon at 6 cubic centimeters per minute. Find the rate of change of the increasing radius when the diameter of the balloon is 10 centimeters. Wow, okay. So, if this is your first time seeing a related rates problem, might be, like, how do I figure out this radius? I'm being given all this information, but how do I do it? Well, this is the thing. When you look at a related rates problem, break it down. So you gotta look at it and find the important pieces of information, and that's what we're gonna do right here. So, two important pieces of information that you can see without even reading this. You can just see our two numbers that are given to us. 6 cubic centimeters per minute. That's the rate at which the helium is being pumped into the balloon, and the diameter of the balloon at which we want to find the rate of change of the increasing radius. Well, we're not done yet looking for important information. What other important information are we given? Well, right in the first line, you can see we're given this very, very important piece of information. A spherical balloon. Now, going back to the previous slide, like I said, the way to go about most of these questions is to look for a relationship between variables. Well, we got a relationship right here. Helium is being pumped into the balloon at 6 centimeters per minute. So the volume is increasing at 6 cubic centimeters per minute. We want to find the rate of change of the increasing radius. So how do we relate these two? Well, we're given this piece of information that it's a spherical balloon. So we can relate volume and the radius of the balloon by the following relationship. Just the equation for the volume of a sphere. Now, students who see this the first time and, after you get a lot of experience, it might sound like a dumb mistake. Try to find, or you start dealing with the relationship between the diameter and the radius, which sounds kind of nonsensical, but when it's your first time seeing this, it gets confusing. I know it was confusing when I first took calculus, but if you get that practice and you just get that experience, and especially that understanding that what you're looking for is a relationship between the two variables, and then expressing one's rate of change in terms of another rate of change, and using the chain rule to differentiate with time, it makes sense. And I'm going to show that. So, like I said, so the helium is being pumped into the balloon at 6 cubic centimeters per minute. So, well, I have this relationship now between the volume and the radius of a sphere, but this relationship isn't telling me how fast the radius is increasing. Well, what do I have to do to find that? Well, I have to take the derivative with respect to time, right? So in order to get a rate, well, I have to take the derivative. And to do that, I need to take it with respect to time and use the chain rule. So let me do that. Let's take the derivative with respect to time on both sides of this equation. Let's take it on the left side. The derivative of volume with respect to time. And I'm going to write it out like this in this notation so it's easier to see. And when you're beginning and starting out with related rates problem, please, please, please use this notation. Don't do V prime and R prime because you're going to get thrown off. Once you get more practice, go ahead, do that. But for now, don't do that. Show that you're, differentiating with respect to time. So let's do the right side now. So 4 over 3, well, pi, this is just a constant. Well, our radius is changing with respect to time. So we got r cubed here. Well, we need to take the derivative of this with respect to time. And what do we have to do? Well, we have to use the chain rule because we got this exponent. So we got to use the chain rule. So we bring down 3. And we got r squared. Multiplied now we got to take the derivative of the inside. And we got to take it with respect to time. So we got dr by dt. We're done the hard work, actually. We're done all the hard work, and usually the hardest part of related rates problems is finding this relationship. And once you get a hang of it, a lot of these questions, they have a pretty, simple relationship. It'll either be a triangle, a cone, it'll be some sort of shape. So it's good to know your formulas for, different types of shapes. Usually they're volumes. A sphere, that's something, very, very common. You should know that one. And, the hardest part is just, finding this in. And then after taking the derivative, after differentiating, it's just a matter of just plugging it in. So let's do that. So we're done the hard part. So now let's just put in our information. So what is dv by dt? What is the derivative volume with respect to time? Well, looking back at the question, well, the helium is being pumped into the balloon at 6 cubic centimeters per minute. The volume is increasing at 6 cubic centimeters per minute. Right there, you see it. Volume over time, dV over dt. So what is dV over dt? Well, it's just 6. Equals, let's do some cancellations here, clean this up. So we got 4 pi r squared. And what's dr by dt? Well, we're looking for dr by dt. Actually, hold on. Substitute another part of information in. What's r? So don't get caught up. People, when they're in a rush, they miss small things, and that is we're given the diameter of the balloon. So what would be the radius? Well, the radius would be half the diameter, so it'd be 5 squared. And then times dr by dt, that is what we're looking for, the change in the radius with respect to time. So you really got to understand what the derivative means when you're doing these problems. Like here, it was the change in the volume with respect to time. Here's the change in the radius with respect to time. So knowing what the derivative means and really understanding it is key to working these problems out and key to understanding how to go about these problems. And so here we go. So we got all the important stuff. Now it's just a matter of isolating. So what does this come out to? Well, this is just, I'm going to clean this up. This is just 6 over 100 pi is equal to dr by dt. There we go. We're done. The rate of change. And this would just be centimeters per minute. Don't forget your units. So there we go. We're done. You got 6 over 100 pi centimeters per minute. That is the rate of change of that's how fast our radius is increasing at when the balloon's diameter is at 10 centimeters. So looking at this problem, just go over it briefly again. What you're doing is you find this relationship, and this is the hardest part usually of these problems, is to find this relationship between these two variables. Then, from there, it's just a matter of just plugging in stuff, reading that question, plugging in the numbers in the right spot, and just solving for your missing quantity, your missing rate of change. So thanks for watching. Hope this is helpful. I'll do more videos and more examples, different examples, common examples, some harder ones too. This video is kind of short because, compared to my other videos, because a lot of these problems are word problems, and I want to go through them slowly, because just, related rates is something that people struggle with. When I was when the first time I took calculus, in high school, actually, related rates is the bane of everyone's existence. But, it's not that bad once you understand it. So thanks for watching. Like and subscribe.